Good afternoon. I would like to start with today's deep learning lecture, lecture number 6. In the previous lecture hour, I first presented a number of data sets for you. They are well-prepared, publicly available data sets, and most of the data sets are typically for deep learning beginners. Small, you even don't need a GPU, and so on. And then I address briefly a number of data pre-processing issues. You should pay attention to all these data pre-processing issues. For example, if you collect your own data set, you need data cleaning. This step is typically not required if you work with MNIST, fetching MNIST, and so on. But still, you need to be aware of, for example, data splitting. The whole data set split it into a training subset, validation subset, and test subset, data shuffling, in order to guarantee that in different epochs that input data, they are not provided to the deep neural network exactly the same order, or data normalization. You should actually normalize the input data into a certain desired data range in order to simplify the training. We would like to address this issue in a later chapter in more details. And data documentation. If you don't have enough data, you should, sometimes you must increase the number of training samples by applying different data documentation techniques. And finally, for classification problems, the class balance. Try to keep the number of training samples for all the classes the same. Otherwise, the majority classes you will be learned quite effectively, but the small minority classes you will be learned not effectively. Good, then I started with chapter 4. I present to you the first type of deep neural network, dense neural network or fully connected neural network. We start with a single neuron. We have multiple inputs. We calculate affine functions of input with a weight parameter, with bias, and we apply a nonlinear activation function to the calculated activation function. So each neuron has a serial and nonlinear behavior. If we have multiple neurons, we can have a layer, a so-called dense layer, a fully connected layer. And the feed-forward neural network, the simplest type of neural network, is just a cascade of different dense layers. Each layer may have its individual number of neurons, individual activation function, and so on. We can easily calculate the total number of parameters and the total number of computational complexity in terms of the number of multiplications. I mentioned at the end that it is important to use hidden layers as a nonlinear activation function jointly. If you use only hidden layers without the activation function, or if you use actually a linear activation function with many hidden layers, there's no actually benefit. Only the joint use is important. So at the end, our neural network is a nonlinear parametric computational model. Parametric means it is described by a large parameter vector containing all the weights and parameters, and it can adjust the model parameter such a way that the output of the neural network matches the desired ground truth as good as possible. So finally, I started to discuss the choice of the activation function. And as I mentioned, we have pretty mild requirements, right? The most important requirement is it should be nonlinear in order to provide the overall system a nonlinear behavior. You should have easy calculation. It should be differentiable. So linear neuron actually means there are no activation function. It's called linear neuron unit step sign function, and the most important one for the traditional shallow neural network, the sigma activation function. how to do the calculation, how to compute the derivative, and finally the hyperbolic tangent function. Today I would like to first continue with the discussion of the activation functions. Then, second topic, I'm going to present to you the so-called universal approximation theorem of neural network. This theorem tells you why a neural network is universal, why a neural net can be used everywhere to approximate some given systems. And then I guess today I'm also going to start with the next chapter, chapter 6 or 5, actually model learning, how to train a neural network. Good. This is actually the topic for today, and we have our lecture number 6, 28 April 2025. Now I'm going to show you the activation function number 6, and this is the most popular activation function in deep neural network, the so-called rectifier linear unit. Rectifier linear unit. The common short notation is ReLU. And this is actually the mostly used activation function in deep neural networks. Actually, the definition is very simple. So the activation function, a phi of a scalar input A, it is written sometimes as the ReLU activation function of a scalar input A. It is defined to be A if A is non-negative and 0 if A is negative. And another short notation in publication you see mostly the notation maximum of A and 0. That's the same. And when I make a drawing, you see immediately the meaning of this rectifier linear unit, phi of A. If A is positive, then the output is exactly identical to the input. If the input is negative, then the output is always equal to 0. Very simple nonlinear activation function. Now, let's discuss some of the property of this rectifier linear unit. Why the name rectifier? The students of electrical engineering, they are very familiar with this kind of rectifiers. You know, probably a very simple electronic device, a diode, with the following symbol. Right, this is an electronic device. If you apply a positive voltage at the input, and this positive voltage appears one-to-one without any change at the output side. If you apply a negative voltage, the negative voltage is completely blocked, and the output is equal to 0. So that's actually so-called rectifier. This is a very simple electronic realization of a rectifier. So you see we have very simple calculations. Simple calculation. So most popular in deep learning. And we can also easily calculate the derivative because we need the derivative later in backpropagation during training. And you know it's very simple. If A is positive, the derivative is equal to 1. If A is negative, the derivative is equal to 0. So this is nothing else than the unit step function of the input. And if you are careful, then you realize this rectifier linear unit is not differentiable at this point, at the origin. Because from the left-hand side, the derivative is equal to 0. From the right-hand side, the derivative is equal to 1. So what is the particular value? Well, up to you. You can say, well, the value is equal to 0 or 1 if A is equal to 0. Mostly, this doesn't happen if you are using a floating point calculation, right? A double precision floating point calculation. The probability that the double precision floating point is exactly equal to 0 has a vanishing probability, right? But if it really happens, you can choose a value up to you. And this also means for negative input, so we have 0 gradient, 0 derivative for negative input. There's no update of our model parameters. We would like to learn this updating in the next lecture. So if the gradient vector, if the derivative is equal to 0, there's no update for the model parameter, and this is of course bad. There's no change in progress, right? We are going to have some feedbacks, and the feedbacks is determined by the derivative, and if the derivative is equal to 0, then there's no change for the current value of the model parameters. And this is exactly the reason why you can find a number of small extensions of the rectified linear unit in the literature. You see on this slide 4 possible variants modifications of the ReLU unit. The one is so-called soft plus. You see the mathematical definition, and you see all of the curve. You see now it is a smooth approximation of ReLU, right? At the left-hand side, so the derivative is pretty small, but it's not exactly equal to 0. Or exponential linear unit. For at the positive side, we still have output exactly equal to input, but now at the left-hand side, if A is negative, we don't have constant 0 for the output. We have very flat exponential functions, and we have no 0 gradient for negative A. So the magnitude of the gradient is still very small, but we have a little bit update of the model weights. The leaky ReLU is widely used in practice because, again, it's easy to implement. No change at the right-hand side, and at the left-hand side, the original ReLU actually returns a constant 0 value, and now we have a very, very slight slope, right? 0.08. So the derivative for positive A is equal to 1, and the derivative for negative A is equal to 0.0. It is still a nonlinear device, but we have a non-zero gradient. And some people even use the so-called parametric ReLU. In this case, the parameter slope 0.01, it is no longer constant for all neurons in the layer, and for all layers, it is a parameter to be adjusted. So the slope is also a parameter to be learned by the backpropagation. And this also implies during the training, at the end of the training, it might be that different neurons might have different slopes. So it increases slightly the computational complexity because we have more parameter to be learned, namely the slope. Typically, we use the same slope parameter for one layer, and we use another parametric parameter slope for the second layer. So this is also used occasionally. But the most popular use is the ReLU. And there are many experiments, and people could show, for example, the all sorts of leaky ReLU. Say, okay, we could show by using leaky ReLU, we can demonstrate this certain benefit, but always quite small benefits. Good. Now I'm going to talk about the last activation function, and this is a very important activation function for classification problem, and this is so-called soft max. If you design a deep neural network for solving classification problem, or even semantic segmentation, this means pixel-wide classification, you always use output as the activation function in the final output layer. We use the notation phi. Now be careful, it is applied to input vector A. It is not a vector defined for scalar input, scalar output. It is a mapping function defined for vector input to vector output. So the vector input is a vector A. Our activation signal, typically in the last layer, containing the elements A1, AI, and so on, I assume it has a length of C. And by using the softmax activation function, the vector A is mapped to another column vector of the same length C. And what's the definition? Phi of A, and many times you see even the name softmax of A. It contains C outputs, and there are C different activation functions. Phi1, Phi2, Phi3, and the different elements that define such a weight Phi of A. So the ith output of the softmax activation function defined to be exponential function of the ith element of the input vector A, normalized by constant, and the constant is defined to be the same exponential function aj, but now j sum up over all the input elements. Very simple definition. But when you take a look at this one, the elements of A can be positive, negative, but the exponential function is always positive, so the denominator as well. So the activation function always returns a value between the range 0 and 1. And remember, the denominator is a constant scaling factor. The denominator is the same for all the indices, Phi, Phi2, and so on. So the output actually is proportional to the numerator exponential function of AI. And due to this very special normalization, we have very easily the following normalization condition, namely the sum of all the outputs of the softmax activation function from 1 to C is always equal to 1. Now, I guess some of you have already the clear understanding. We have an output vector of length C. All the elements they are non-negative between 0 and 1, and the sum of them is equal to 1. They are probabilities, right? Actually, by using the softmax activation function, we calculate at the end the final output of the neural network is a probability vector for C classes. It tells us the particular input image, the particular input speech signal belongs with this probability value to the first class and with the next value to the second class and so on. This is actually the estimated probability vector for classification problems. So I'm going to give you some comments. You see, if AI is very large, much larger than the other elements, then you see that the corresponding output is close to 1, right? We are almost sure that the input image contains a cat, something like that. And if AI is very small, much, much smaller than the other one, very large, very small, then you know it is close to 0. And this softmax activation function is always used in the output layer. That's a last layer with a layer index capital L, in the output layer to calculate the probabilities for only classification problem. We never use softmax for regression problem, but we use softmax for classification problem, for semantic segmentation problem. In semantic segmentation, we even calculate the probability vector for each pixel, right? Because each pixel may have different probabilities belonging to the C classes for classification. And finally, the final comment is, by using softmax, we perform actually a nonlinear normalization of the input elements A. So it is actually a nonlinear normalization of the input vector A. The input vector A, the elements of A can be positive, negative, they have no physical interpretation. But after softmax activation function, we have now a probability interpretation because the outputs they are between 0 and 1, and they sum up to the total probability equal to 1 decimal. So this is the last activation function, and now I have a simple example for you. Let's take a look at the softmax activation function. This is once again our deep neural network. That's the input to the first layer. That's the input to our neural network. Remember, that's a final layer with xl minus 1 as the input and xl as the output. And of course, again, we first calculate a affine function, WL times xl minus 1 plus BL. This is our activation signal. And then we apply this vector-to-vector softmax activation function once again by using this formula. Assume we have a 4-class problem, so we need 4 output neurons, and assume that the activation vector in the final output layer is given by these 4 numerical numbers, 1.28, and so on and so forth. And after the softmax activation function, we have the probability values, the input belong to the first class with probability 20%, belong to the second class with 0.2%, to the third class with 74%, and to the final class with 5.5%. Of course, this one is a winner, but we see the winner already actually in the input side. Why? It's because 3.1 is the largest one than the other one. But after this normalization, we have a probability measure. Well, we have a decision with 74%. So this is actually the so-called activation function. Good. I go back to the previous slide because I have some additional properties, namely the derivative. We also need to calculate the derivative of the softmax activation function, softmax. Remember, we have multiple inputs, we have multiple outputs, and we need to calculate the partial derivatives. So the partial derivatives of the i's output with respect to the j's input j. So indices I and j, they can be different, they can be the same, right? We need to calculate actually in this position the so-called Jacobi matrix. I jump over the details, and the final results they are pretty simple. For the case I equal to j, and for the case I different from j, we have 2 different results. For I equal to j, we have a similar result, just like the derivative of sigma activation function, phi I of a times 1 minus phi I of a. The formula looks exactly just like for sigma activation function. If I and j are different, we have only the cross terms minus phi I of a times phi j of a. So this means you can easily calculate any partial derivative by using the normal outputs of the softmax activation function. That's all. Now I'm going to discuss a final spatial case. What happens if we have a binary classification problem? In binary classification problem, we have, of course, a total number of 2 classes. Male, female, cat, dog, spam, non-spam, and so on. And of course, in theory, we still need a softmax activation function for the nonlinear probability transform with 2 inputs and with 2 outputs. But I'll have to show you in the next few minutes that for the spatial case, you can replace the 2 input, 2 output softmax activation function with an even simpler sigma activation function you have learned last time, because the sigma activation function has only 1 input and 1 output. This equivalence is only given for the spatial case of binary classification problem. For more than 2 classes, you always need softmax. For 2 classes, you can use softmax, but most people use the sigma activation function. And the equivalence is quite easy to show. If we use actually softmax, we have 2 outputs. The first output is given by, based on definition, exponential function of the first input normalized by the sum AE1 plus AE2. That's the definition. I can divide the numerator and the denominator by the numerator in order to force value 1 in the numerator. 1 plus A1 exponential A1 minus A2. It's the equivalent row formulation. And this formula is well known to us. This is nothing else than the sigmoid activation function now with the input A1 minus A2. So the softmax calculation can be computed easily by using sigma activation function. What's the second output? Well, we don't need any calculation. By normalization, we know the second output is 1 minus the output, the first output tensor. And you know the probability, we know the property of the sigma activation function. It is nothing than the same activation function sigmoid, but we change the order A2 minus A1. So this implies, I'm going to use the next bigger slide. This means now we have the equivalence. For binary classification problem, theoretically, you can still use the softmax. It's not wrong. With 2 inputs, A1 and A2, with 2 outputs, phi1 and phi2. And you know, phi2 is nothing else than 1 minus phi1. And this calculation can be replaced by a simpler sigma activation function. You provide the difference between A1 and A2 as input. And now we use a sigma activation function. And the output is a sigma activation function of A1 minus A2. And this is by definition the first probability phi1. And you don't need to calculate the second probability if you know, okay, the probability for male student is 70%, then the probability for female student is 30%, right? It's quite clear because it's a binary classification problem. If you have a multi-class classification problem, this is no longer so trivial. This means 1 output with sigmoid is sufficient for binary classification problem. It is simpler than to use 2 times 2 softmax activation function for binary classification. They are the same. Okay, now I have presented to you a large number of activation functions, and the most activation function you will see they are contained here. Occasionally, you will see a few new activation functions. I would like to say 99% of activation functions they are covered in this discussion lesson. And at the end of the section, I summarize all the results on the following slide, named activation function, when and where to use which activation function, when refer to the application, regression problem or classification, regression in this column, classification in this column, where means in which layer we distinguish between hidden layers and the final output layer. And you see, in the hidden layers, we can use theoretically any nonlinear activation function, ReLU, sigmoid, sine, and hyperbolic tangents, and so on. But the ReLU is a standard used today, right? Sometimes even the leaky ReLU is used. And in the output layer, for regression problem, we use the identity activation function. Identity activation function, you means we don't use any activation function. We just output the activation value A without any additional nonlinear transform. Because the reason is very simple. We already have enough non-linearities in the hidden layer. There is no need to apply additional nonlinear activation functions in the output layer. We can keep the output layer as simple as possible, but we provided we have at least one or multiple hidden layers with a nonlinear behavior. In the classification application, again, you can use any nonlinear activation function for the hidden layers. Again, we mostly use the ReLU activation function, but in the final layer, we must use softmax activation function in order to change activation signals A into a probability vector. So keep this table in mind concerning activation functions. Good. You have learned the basic architecture of a dense neural network. The choice of the activation function is actually not so complicated. And now we are going to learn the so-called universal approximation theorem. Universal approximation theorem. This theorem explains why can neural network be used everywhere to solve all kinds of problems. Universal. A few lectures ago, as I introduced to use a framework for machine learning, you know, we have the real world and we have actually a machine learning system. The machine learning system uses a parametric computational model, which is typically nonlinear, to calculate a certain output and so on. And actually, for the parametric machine learning model, you can use any architecture. If you attend the core detection pattern recognition, you will have to learn later support vector machine, random forest, Gaussian mixture model, k-nearest neighbor, and so there are so many different architectures. And neural network is one possible nonlinear architecture described by parameter vector, right? But today, in AI, in deep learning, it turns out that the deep neural network was the most popular nonlinear architecture. The question is, why? And there's a very simple answer for this question, and you see the answer now on the next slide in terms of the universal approximation theorem. It tells us a feed-forward neural network with a linear output layer. This means, again, we don't apply any activation function in the final output layer, contain at least one hidden layer, and this one hidden layer should have a nonlinear activation function, can approximate any continuous nonlinear function to arbitrary accuracy. It's very simple, but it's a very impressive result. even if you use one hidden layer with a certain nonlinear activation function, this very simple architecture is already able to approximate any smooth nonlinear system to arbitrary accuracy. What's the meaning to arbitrary accuracy? Namely, with increasing number of hidden neurons. The larger the number of the neurons you use in the first hidden layer, the better the approximation. That's the meaning. And this statement is even true for a wide range of nonlinear activation functions. It's valid for all activation functions I present to you in the last actually 10-20 minutes, excluding polynomials. Because polynomial has a very undecided behavior, it diverges very quickly. If you study x squared, x to the power 3, and so on, the function diverges very quickly. We need actually bounded output behavior. You know, our actually real linear activation function, it just increases linearly. But sigma activation function, hyperbolicus, tangent tensors, they have always a smooth, nonlinear, but bounded output behavior. And the minimum requirement for the universal approximation is very simple. We have one hidden layer with a nonlinear activation function. X0 is the input. We calculate a fine function. Then we apply suitable nonlinear activation function to the output. This is the input for the second layer, for the final linear output layer. We just calculate again a second affine function without any activation function. This formula is enough to approximate any given nonlinear function. I'm going to show you one example later. So it's a very impressive result, but this theorem is also sometimes misleading because the result, the statement of the theorem is both strong and weak. Strong means universal approximation. Weak means it just tells us, I can guarantee you there is a solution. It's an existence theorem, but does not tell you how to find it. It does not tell you how many neurons are required to find a solution, right? We are happy to know, okay, there's one solution, but we will be more happy if we know how to find it and with which complexity it is. I mentioned a few decades ago, as I was a PhD student, there was so-called the first Renaissance time. In that time, actually, many people started also shallow neural network with only one or two hidden layers. They never started neural network with more than two hidden layers. What are the reasons? There were multiple reasons. At that time, there was no large data set. There was no GPU, no computational power. But the one major reason is this universal approximation theorem. It's misleading. It tells to the research teams, don't worry, one hidden layer is sufficient. They try to find a solution with actually one hidden layer. But today we know, of course, you can solve the same problem with one hidden layer or with 10 or even 50 or even over 100 hidden layers. You have learned deep networks are better than shallow ones. By using a deep architecture, you can easily find a good solution. By using a shallow architecture containing only one hidden layer, it's very difficult to find the overall mapping. If you use a deep neural network, each mapping realized by each one layer is very simple, but the deep cascade is quite complicated. And we even know today, theoretically, you can use any of the presented activation functions, but we know today some activation functions are better than the other one, better in the sense we can easily find the solution. It does not violate the existence theory, right? There is a certain solution. Now we are talking about how easy is it to find the solution. So it just tells us the existence, but we are actually interested in architectures where we can easily find the solution. Then we prefer to use deep architectures, and we prefer to use some activation function than the other ones. So this is actually a difference. Now I'm going to show you, to give you a little bit feeling, why do we have this very impressive result, I'm going to show you some derivations and then later one numerical example, one computer experiment example about regression with a single hidden layer. That's a simple architecture. So assume the true function to be approximated. It's a very simple scalar function given by f0 of x. It maps a real-valued input to real-valued output, one input and output. And what's a data set, training data set? I assume to know the true functions that the ground truth, and I use the ground truth to generate some random samples, super labels random sample x of n, and noisy output y of n. Y of n is nothing else than the output of the true function applied to x of n plus some random noise, right? And assume to have a total number of capital N training samples. And now I use a very simple dense neural network containing only a single hidden layer. We have a single input. X0 is a general notation for the input of the whole neural network, in our case just x. This is our single neuron. We have a single output neuron. This is actually our output x2. And we assume we have a hidden layer containing some hidden neurons. And we have fully connected architecture. So I assume this is actually the output x1. I assume we have M1 hidden neurons. And I assume the sigmoid activation function, just for example, sigmoid activation function. So the first activation function is the sigmoid activation function. And for simplicity, as I assume the second layer has no activation function, so the second activation function is an identity activation function. This means actually we don't apply any activation function. And now we have here a single input and a vector output, so this weight matrix simplifies now to a weight vector W1. And the bias vector is the bias vector for the first layer. We have here, for the second layer, we have input vector, output scalar number, and then we also have weight vector for the second layer, and we have a scalar bias because we have only one output neuron. That's all. So far, this is the architecture of our very simple neural network containing only one hidden layer. Now we can derive the mathematical relationship. I can formulate the overall output x2, the output of the network, as a function f of the input overall input x, and this function f described by the neural network is determined by the model parameters theta containing all the weight parameters and bias. And mathematically, we can use the following notation. In the first layer, we first calculate a affine function, W1 times scalar input plus B1. That's activation signal of the first layer. Then we apply our sigma activation function element-wise to this vector. And this is the output vector of the first layer. Then we study the second layer. It once again calculates a affine function, the second weight vector, but now actually in inner product with output vector plus B2. So this is a mathematical description of this overall neural network. In vector notation, I can also reformulate this overall result in element-wise notation. Say I sum up over all the hidden neurons from 1 to M1. So the ith element of the second weight vector multiply the ith element of the output of the first layer, and this is nothing as a sigma activation function applied to the ith element of the first weight vector multiplied with the scalar input plus b, I, and then plus b2. This is actually an element-wise notation. But now we take a look at this formula. You see the overall network output can be written as a linear combination of M1 nonlinear base functions. M1 nonlinear base functions of x. So the output of the network can be written as a linear combination of a large number of nonlinear base functions. And the shape of the base function is, of course, determined by the sigma activation function. You know the function, sigma activation function, between 0 and 1. We have a smooth increase from 0 and to 1, symmetric around the point. But now our base function, the sigma activation function, is applied to something else. When I take a look at the formulation sigma activation function, I would like to say W, I ignore all the indices, x plus b can be written as sigma activation function W x plus b divided by W. It's a reformulation. So this means we shift the center of the sigma activation function, new center. So new center is now at the position of minus bias divided by the corresponding weights. And although the slope is changed, we have a new slope of the sigma activation function, namely determined by the parameters W. Now I can make a drawing of all these nonlinear activation functions. Remember, all the weight parameters W and BZ are learned. You can't take any possible values. For example, for the first neuron, the sigma activation function is shifted to the right-hand side and multiplied with a number larger than 1, so we have very steep sigma activation function. For the second neural network, W can be negative, small magnitude, then we have a very flat, but to the left shifted sigma activation function. And the third activation function looks once again something different. And the fourth activation function once again. And you can imagine we have a large number of different base functions, all from the same shape, activation function, sigma activation function, but with totally different slope, but different offsets. And at the end, when we compute the linear combination of all these base functions, then we can approximate any given nonlinear relationship by using this linear combination. So this is actually the activation function Wi x plus bi j. So this is not a mathematical proof, but it should give you a feeling about that one, what happens really by this network. And now let's take a look at the first Python compute experiment in this lecture, a very simple regression problem. I assume the true function f0 is given by sine of 1 plus x squared. This is represented by the dashed black curve in the interval between 0 and 3. Now I generate my training data set, I generate total number of 100 noisy training samples. I randomly sample 100 samples x of n in the interval between 0 and 1 uniform distribution. And for each xn, I calculate the true value of f0 plus an additive zero mean white Gaussian noise with a standard deviation 0.1. And this is my actually y of n. Y of n represented by the blue dots. I have actually 100 blue dots representing 100 noisy training samples. Noisy because all these blue dots are not located exactly on the black dash curve. In the first experiment, I use a single hidden layer with only 10 hidden neurons and 1 equal to 10. Of course, we have a scalar input, we have scalar output, and that's a final result of the training process. And you see once again here, the 10 base functions of the 10 hidden neurons, right? Each base function implies a certain shifted center, a certain change slope. And you see the regression result is not good enough. It can approximate some behavior of the input-output, but that's not perfectly, because we have only used 10 hidden neurons. So we can increase the number of hidden neurons because theorem tells us to arbitrary accuracy. Now we can increase the number of hidden neurons to 100. Again, the red curve represents regression result using 10 neurons. The green curve represents regression result using 100 hidden neurons. You see, in this region we have a much better result. Even in this region we have a much better result, but here we still have some problem. So actually, the larger the number of the neurons, the better the approximation, but it's not good enough. Of course, you can see I can try with 1,000 neurons. Yes, you can do that one, but the better idea is to use a second hidden layer. I did that one, a second hidden layer with only 5 neurons, right? The first hidden layer still uses 100 neurons, but the second layer has only 5 neurons. Very minimum computational complexity overhead. But now you see the last curve, the green is the blue curve. The blue curve almost approximates the true function perfectly. Much, much better than the green one with only additional 5 neurons, but on the second layer. When I spend the 5 neurons in the first layer, you can expect no serious difference, but the second layer, it is much better. Good. This is so-called universal approximation theorem. It only tells you the existence of such a solution, but you know today, in addition to the dense neural network, we are using convolutional neural network, recurrent neural network, and recently we are using transformer because we know theoretically we can solve all problems with only a very, very large hidden layer. But typically we know using other dedicated architectures, we might even solve the problem more efficiently. So that's the reason for the study for different efficient architectures. Good. This is actually the summary of chapter 4, dense neural network, pretty short chapter. It tells you the architecture of the dense neural network. I introduce the weight, spice parameters, even some hyperparameter, namely the activation function, the number of neurons, different activation function, and universal approximation theorem. So before I switch to chapter 5, model learning, any questions to chapter 4? Good. Then we now are ready for the next topic, model learning. So step for step. You're now familiar with the training data set. You're now familiar with a simple computational model, a dense neural network. Now we talk about how to learn the unknown model parameters from the data set. Now, given a training data set, given a deep neural network architecture, up to now you only know the simple fully connected neural network with a certain model parameter vector with model parameters theta. It contains all model parameters we would like to learn from data set. Now the question is how to design a loss function. And this is actually a topic of the objective engineering. Objective means we design the objective of the optimization problem. What's the goal, right? Objective engineering, objective and the second question is how to learn the model parameters. And for this case, in addition to the objective function we choose, you need to select a suitable optimization algorithm called optimizer. You also need to define a suitable time schedule how to do the optimization, iterative optimization. That's a so-called training engineering. Remember, I mentioned deep learning contains multiple engineering components. Up to now, you have learned data engineering, architecture engineering, now objective engineering, optimizer, and training engineering. Once again, I would like to review the issue of loss and cost function. We have already started to look at the loss and objective function in Chapter 2, Machine Learning Basic in the probabilistic framework. We started with our KL divergence, and we say it's equivalent to the minimization of the cross entropy. Then we use empirical distribution. At the end, we have a formula for the cost function. It is the average of the loss function over all training sample, and the loss is so-called negative log-likelihood loss. But then we stopped the calculation because we have no idea how do the approximating function Q looks like. It depends on the architecture. It depends on the deep learning task. So we would like to continue with this development of loss cost function now in this chapter because we know now actually the architecture. We can assume a specific formula for the approximating log likelihood, then we can calculate the particular loss and cost function. This is actually the second part of the loss and function. That's all. But at the beginning, I once again want to make a big diagram drawing to illustrate the overall procedure. This is actually the overall input x0 for our deep neural network. That's the input sample from our training data set. Then we have any architecture of our deep neural network. Its behavior is described by parameter vector theta, which is unknown, which has to be determined. And this deep neural network returns, of course, a certain output value. The output value can be written as an estimate for the output. It is nothing else than the output of the final output layer with a layer index L, or we can say it is actually the function f of x parameterized by the parameter vector. So we have multiple notations for the final output. And now we need a loss function, a loss of x and y. We use a loss function to compare the actual output of the neural network with the ground truth for that particular input coming from the labeled data set. This is actually our loss function or cost function. And we see some difference, and the difference is actually used to adjust the model parameter. That's the overall picture of learning, of model learning. It's important to remember, I already mentioned that this situation is very similar to your study at the university, right? You need some inputs for your study. It could be textbooks, it could be video recordings, it could be some lecture notes somehow. So deep neural network is comparable to the knowledge transport mechanism for study at university. Could be lectures, could be exercises, could be seminar, could be lab. And we need regularly control of your learning progress. We use exam. We use exam to compare your particular output in the exam with the upper bound. Upper bound means sample solution of the exam. Most frequently, we see some difference. For some students, small difference. For some students, pretty large difference, deviations. And these differences, they should be motivation for you to refine your learning skill, to improve your knowledge. And this one is an iterative procedure. So the model learning, machine learning, is very comparable to learning in the school, learning at university. It's not a big secret. And now we review a result from our development in chapter 2. We try to minimize the so-called cost function L, a function of the unknown parameter vector theta over L. And this is defined to be the arithmetic average over all training samples and to L of a so-called loss function. And the loss function is now calculated position of the nth input-output pair. And the loss function depends on the architecture, depends on the parameter vector. This is actually our cost function. And the loss function defined for one generic input-output sample pair, it is given by minus log likelihood loss. It's an approximating conditional distribution for y conditioned on particular input x, parameterized by the parameter vector. This is actually our negative log likelihood loss for one sample pair. And we stopped the calculation in chapter 2 because we have no idea how does this approximating likelihood look like. And now you would like to see the calculations in chapter 2 are general. It's framework. It's valid for regression, for classification, for semantic segmentation. It is even valid not only for machine learning, but also for statistical signal processing. But now, in chapter 5, you would like to see the approximating of likelihood changes from application to application. You would like to see the function Q for regression, for classification, for semantic segmentation, and for even object detection. At the end, you will have different loss functions for different applications. So that's the reason we can only discuss the second part of the loss calculation now in the chapter number 5. And we first start with the simple applications regression problem, and then continue with the classification problem, regression. In regression problem, we know our input x is any d-dimensional input vector. It's a random vector. And our desired output y is also represented by a real-valued random vector, actually c-dimensional. It's a desired output. Right? The input is a face image of you, and the output is we want to estimate your age, right? This is actually the desired output. And you know your age. You can take a look at your personal ID. And now, what's the function of Q? And what's the role of the deep neural network? Now we make the following assumption. Namely, our neural network D and N returns a certain output. And the certain output has a physical meaning, returns a mean of the random output Y as approximation. So mathematically, we say that the desired output Y, our random vector, can be written as the output of our neural network calculated for a certain input determined by the model parameter vector plus a certain Z. And the output can be also written as the estimate Y hat. And Z is called typically noise, but in our case, it's not really noise, just a sensor noise and so on. This is nothing else than approximation error. We can never perfectly predict the value of output of the ground truth because it's random. So for example, when I ask 10 people to speak good morning, in the same way, I will have 10 different speech waveforms. They always look the same. They always look somehow similar. Right? But different people have different speed, intonation, breaks, and so on. You will have 5 or 10 similar speech waveforms, but containing the same content. So we can see our output estimates the deterministic mean, but we have no control about the so-called noise. And now we can assume actually a distribution for the noise. And I'm going to study 3 cases. The first case is standard case. Most people assume the following situation. They assume Z is Gaussian distributed, zero mean, with a scaled identity matrix with the covariance matrix. And we mostly see it is actually white Gaussian noise. Gaussian noise because the distribution is normal distribution, Gaussian distribution. White because our covariance matrix is identity matrix, so all the random elements in the vector Z are independent, uncorrelated with the same variance. This also implies our output Y conditioned on the particular vector input X. It is also Gaussian distributed. If X is given, then the estimate Y hat is given. It is actually the mean of the Gaussian distribution with the same covariance matrix. And now I'm able to formulate my approximating likelihood. The probability density function of Y conditioned on X is given by the well-known formula of the multivariate Gaussian distribution. You have 1 divided by 2 pi sigma square to the exponent c divided by 2c is the number of the elements in the output vector. And then we have our famous exponential function, 1 over 2 sigma square. In our case, the random vector y minimize the mean vector. The mean vector is given by the output of our neural network squared or Euclidean length. Under the assumption that the output of a neural network represents the mean of the desired output, under the assumption that the approximation error Z is Gaussian distributed, then we have the following likelihood. Then we can easily calculate the negative log likelihood. Of course, this is only assumption. When you calculate the approximation error, you would like to see it is not really Gaussian distributed, right? The thermal noise is Gaussian distributed due to the central limit theorem. There's one mathematical motivation. This is not really Gaussian distributed, but we need an assumption in order to be able to formulate our loss function. And now I can calculate the loss value, right? I can calculate the negative log likelihood loss for given x, y determined by theta. It's minus natural logarithm of the approximating distribution. This is actually given by the PDF function of Gaussian distributed random vector. So you have a scaling factor. It's a constant term. We ignore the constant term. Then you have the exponential exponent. The log function and exponential function, they are cancelled out. You have the scaling factor in the exponent. And then you have, at the end, the squared or Euclidean length of the difference between the gram truth and the neural network output. Once again, we ignore the scaling factor. And this is actually the loss term for one sample, and the final cost function is, of course, the average of all training samples, namely y of n, the nth training sample minus the output of the neural network, calculate a position of the nth input sample and theta squared or Euclidean length. And this is the first possible. This is the first possible cost function, final cost function to be minimized for regression problem. And we call this one the so-called mean square error loss, mean square error. This is the most popular name because we compute the squared error and average over all training samples. This gives the name mean squared error loss. And if you're familiar with the different vector norms, in chapter 2, I introduced L2 norm, L1 norm, L0 norm as a vector, This is actually also the so-called L2 norm. L2 norm is just identical to the Euclidean length of a vector. So this other reason is so-called L2 loss. Sometimes people say L2 loss. Or if you are starting parameter estimation, or you can see it's a so-called least squares method. The least squares method was invented by the German mathematician Gauss, right? Not for deep learning, for actually calculating an orbit. Least squares method. You try to minimize the sum of squared differences between the model output and the actual output. There's a so-called least squares method. Many different names for the same criterion. This is the objective, mostly used in regression problem. The question is, how can we now determine the optimum parameters, theta? Depends on the function f. So I'm going to give you now one comment. In the course statistical adaptive signal processing in the winter term, not in the I discuss linear and nonlinear least squares method in details. It tells you if the function f is a fine function in the parameter vector, then we have a closed form solution for theta. This is, of course, a beautiful situation, but it's only happened if f is a affine function, can be written as a linear combination of theta plus a parameter vector. But we are dealing with multi-layer perception. We are dealing with deep neural network with nonlinear activation function. In this case, our function f is definitively nonlinear in theta. So in this case, there is no closed form solution. We need iterative minimization. Iterative minimization. I'm going to talk about the iterative minimization in the next lecture hour. The most popular method is called stochastic gradient descent. Good, that's case A. Now I'm going to show you a case B, and later on the slide a case C. We can also assume, for example, that approximation error is still Gaussian distributed with zero mean vector, but with any non-covariance matrix. This one is called colored Gaussian noise, no longer white. Colored Gaussian noise because all the elements of the random vector Z are no longer uncorrelated, no longer independent, because the off-diagonal elements of CZ may be non-zero. Then, in this case, we can still do the same calculation, and at the end, we end up with a slightly different expression for the final cost function, because the loss looks slightly more complicated. Namely, we have again the difference between the desired output and the actual output, x of n calculated as a position of the parameter vector. This is a column vector transposed to a row vector multiplied with the inverse covariance matrix, have the same difference vector once again. And this is no longer the mean square error loss, it's a so-called weighted mean square error loss. For example, assume C is a diagonal covariance matrix, but with different diagonal elements, and you would like to see different elements in the weight vectors will be multiplied with different diagonal elements of the covariance matrix. So we pay more attention to some elements of the error vector, we pay less attention to the other one. So the covariance matrix is introduced to do some weighting in the mean square error loss. But this one is, in practice, rarely used. The question is very simple: how to choose the covariance matrix. The simplest choice of covariance matrix is scalar identity matrix, then we have our mean square error, right? If you have a good idea, if you have some intuition, so the covariance matrix should be this one, then you can use your actually selected covariance matrix. That's all. And finally, I have even a case C for you. Depending on the assumption, now we assume we have a Laplace distribution, and then you would like to have the L1 loss and no longer the L2 loss. I've reviewed the Laplace distribution also in Chapter 2, Machine Learning Basics at the very beginning, and now we have again the same assumption. So the desired output is the sum of the output of the neural network plus the approximation error vector. Now all the elements of the approximation error vector, they are independent, identically Laplace distributed with zero mean with the parameter b. And we know the Laplace distribution, it's exponential function with a magnitude of y minus f, no square, just a linear function actually in the argument. Since all the elements they are independent, the joint distribution for the vector y can be written as a product of the marginal distribution for the individual y, and the product can be reformulated to a sum. Now I can once again calculate the negative likelihood ratio or loss. And after some calculation, you see we have the sum of the magnitude of all the elements. And this one is called the L1 norm in the course Advanced Mathematics. We are not computing the sum of squared elements. That's L2 loss, L2 norm. We are computing the sum of the magnitude of the elements without any squaring. That's a so-called L1 norm. So that's the reason for the name L1 loss. Another name is mean absolute error instead of mean squared error. There's no squaring. We only calculate the magnitude, the absolute value of the error, and then we take the average over all training samples. So you see, you can choose the mean square error loss, you can choose the mean absolute error loss from PyTorch. It depends on you, right? You would like to see which one is better. It's hard to say because each loss is optimum in a specific sense. But regardless of the loss you are choosing, in all cases, we are minimizing the difference between the desired output and the actual output in a certain sense. But the sense is different. In one case, the sense is a L2 loss. In the other case, the sense is a L1 loss. Now you see actually how do we get the so-called loss and cost function for the regression problem. One final comment for the regression problem. Cost function we use is exactly equal to the performance matrix during performance monitoring. The performance matrix are used to see how good the learning progress. Of course, the smaller the value, the cost function, the better the matching of the neural network to the given data set. We use the same value of the cost function during training also as the performance matrix. But this is the case for regression. You will have to see later in classification, cost function, performance matrices are slightly different. Good, that's a simple case. Now we are going to discuss the next deep learning task, classification. You would like to see now we will have a totally different approximating function Q, and we end up with totally different loss function, the so-called categorical cross-entropy losses. Now we take a look at the second application classification. In total, we would like to discuss 4 different application: regression, classification, semantic segmentation, and object detection. These are the 4 most popular deep learning tasks. Classification. So once again, we assume we have again a vector input, d-dimensional, its input. And now what does the desired output for classification problem? We already discussed this issue in details in the machine learning basic chapter 2. You can use an integer class label, class 1 to 10 for the 10 digits. But we prefer to use the so-called one-hot coding. Now you would like to see the benefit of the one-hot coding now. In the one-hot coding, the class label is not an integer, it's a vector. It can be the first unit vector, the second unit vector, or the last C unit vector. They are the class label for our input vector X. The input vector can be speech, can be image, can be anything, right? But now it's in one hot coding. Remember, we introduced the one-hot coding in order to have a compact mathematical expression for the probability mass function. And you know, NZ Pi, it's nothing else than the true probability that the input x belong to the class I, namely the target label y is equal to the i's unit vector conditioned on a particular input. This is actually the true posterior we are looking for. And in our chapter 2.2, by using the one-hot coding, we could formulate actually our true class input conditional probability mass function to be the product pi to the power of yi over OC classes, over C bits, right? This is actually our true probability mass function. But in real-life application, we don't know the individual probabilities, unknown. We have to estimate these probabilities. Given a particular input image, I want to know, is this actually a cat, a dog, and with how much probability? So this is actually the situation. Now let's take a look at our deep neural network once again. Now the output of the neural network has a totally different interpretation. No longer the mean output, rather the output of our neural network f of x containing the elements f1, f2, and so on. We have a vector output fi x theta. It's a vector notation. It is also a c-dimensional column vector. It is an estimate for the unknown probability vector. Unknown probabilities with the elements pi, pc, and so on. So this implies now we have a formula for our approximating distribution Q. This means the unknown probability mass function we are looking for is again approximated by my neural network. Approximated by my neural network Q. Y conditioned on X. The Q is determined by our neural network, again with the parameters. We have the same formula as previously. We have the product over all the classes. But instead of the probability value pi, we don't know. We just write the ith output of our neural network, x parameter theta, and times yi. Now who can tell me, I want that my output of my neural network for classifications behave like probabilities, and you know all the output should be between 0 and 1, and the sum of all these outputs should be equal to 1 due to the normalization. How can I achieve this one? How can I force the neural network to provide this kind of probability values? What's the measure? How can I force a neural network to provide this kind of probability-like outputs? Softmax. I introduced a softmax. The softmax is only designed for this purpose, that's all, right? So this is a softmax in order to ensure we need actually the properties, namely all the fi between 0 and 1, and the sum of all the fi is equal to 1, right? Softmax is used in the final output layer. Now you know the reasoning for the output layer. So the final output XL It's the overall function f of the input x determined by the parameter vector. It is nothing else than the softmax applied to the activation signal L in the last final layer. And I introduced actually the softmax in the previous chapter roughly 30 minutes ago. And now I'm going to calculate the final loss. The loss value L for any input-output pair is once again defined to be minus log likelihood Q, the big Q, y conditioned on x theta. And now you put the formula into this one. We have a log function, we have a product, and the log function changes the product to a sum. We have minus sum over OC classes. And then yi is a ith element of the class label. Since we use one hot coding, yi can be 0 and 1 times log of the ith output x and theta. I prefer to use a short notation, namely f denotes vector output for a particular input. They apply the log function element-wise to the vector output. This is actually a column vector, and this is nothing else than the scalar product of the class label in one hot coding y times log of the output, it's minus. And this is always positive because the probabilities they are always actually negative, and between 0 and 1, a log of a number smaller than 1 is always negative. We have a negative sign, so actually this one is equal to 0. And this one is called, so the final line today, you can say this is called the categorical cross entropy loss. So in classification problem, you should use a totally different laws across categorical cross entropy laws. Next time, I would like to explain it is still possible that you can use, for example, the mean square error laws, but mostly the performance is much worse than using the categorical cross entropy laws. Next time, I'm going to further discuss loss functions for semantic image segmentation for object detection. Then I'm going to dive into the topic how to train the network by using which stochastic gradient descent procedures. Okay, don't forget, on this Thursday, we have again a public vacation. We have so many public vacation days in Germany, so see you next Monday.